Well, good afternoon, everyone. I'm Allison McKay. I'm the chair of the Civil, Environmental, and Geodetic Engineering Department at Ohio State. It's my pleasure to welcome you to this next CEGE CONNEXT lunchtime seminar series. There is a lot of amazing and creative research that is happening in our department right now, and the value and impact of this work is most fully realized when it's informing practice and policy. This CEGE CONNEXT series is an opportunity for you to hear from faculty as they share their perspective on recent innovations that are relevant to practitioners. And we're always happy to reconnect with you both today and also later to highlight that the CEGE department is a resource for you even after you graduate. It's my pleasure today to introduce Dr. Alper Yilmaz, who's an expert in photogrammetric, computer vision and navigation. He is an entrepreneur who has founded a company, You Be Here, and it uses biomimetic navigation systems for asset management. He's got test beds with organizations that are in healthcare and the military. And this, among other work that he has been done, has contributed to his recognition as the Innovator of the Year at Ohio State University in 2020. And also in that year, he was later inducted into the U.S. National Academy of Inventors. So I'll ask that you please drop questions into the chat function at any time during the presentation, and I will moderate those in the question and answer session at the end of Dr. Yilmaz's presentation. So let us welcome Dr. Yilmaz.
Thanks, Allison, for the nice introduction. Welcome, everyone. Thanks for making the time to listen to this talk. It's going to be a little bit different from potentially some of the talks that you had been engaged with over the past several months. So we will be focusing on autonomous platforms in this talk. And, Tesla has been rolling out these autonomous driving platform and is in a beta form that people have been using. So we'll kind of look at that from a little bit different perspective. So there are some things that are on the research front here. Some of these things are actually on the non-research front, which is on the product front. But the whole point of this is to figure out how mammals perform this, and then how they can mimic their performance into autonomy of different platforms in the air, on the ground, or in the water. So, okay, all right, I think yes. So why do we care about this problem? So number one is obviously we'd like to have a better traffic performance. So if everything's autonomous, you won't have these bottlenecks you don't even need traffic lights. So that's one thing, right, on one end. But in general, you can use these platforms for planetary endeavors. And there has been an endeavor actually on Mars that has been collecting data for so many years. We are sending another platform to Moon, and human navigation is going to become an issue, especially in the dark side of the moon. So that becomes something that we will be interested in moving forward to do research on. And also you can provide these systems as an assistive tool to visually impaired people so that they can actually navigate easily on the roads or on different inside the malls and other places. So there has been significant work in the physiology side, right? So people have been working on this for about 80 years now, and actually beyond 80 years. But the most important steps in understanding of how mammals perform navigation started about in 1940s. So they understood that there is a cognitive map the brain develops, but there hasn't been much development after that. In the 1970s, they came up with the concept of a place cell. Turns out it's a neuron that figures out where you are if you recognize a landmark. And then in the 90s, head direction cells, and in 2005, the grid cells were found. So this led into a Nobel Prize in 2014 that was shared with this couple, Moser couple and O'Keefe, which actually figured out how the brain on the hippocampus maps the environment and figures out how you move from one location to another. This was revolutionary. So our research has been built up on these kind of recognitions that has been done in the field of medicine. So if you look at a mammal, it's humans, or it can be bats, or, there has been a lot of work with mouse. So when you put these in the field, what they do is they like to first understand if this is an unknown field, they had never been there before, they first try to figure out how they can recognize where we are, how they can traverse the environment. So there are certain cells, the way they did it was to put actually electrodes inside the brain to see if a neuron fires. A neuron fires is a positive voltage that they can be measured. So they look at these firings and notice that if a mammal, in this case a mouse, recognizes a certain position, a landmark, a place cell gets fired. If the mouse goes into the boundary of some place that is either dangerous or there is the environment ends, another cell fires. That's called a boundary vector cell. And then as the mammal traverses the scene, it actually generates a grid-like structure. And this grid-like structure is a hexagonal structure that are highlighted by the grid cells. So now, looking at this, and it's a very complicated system. I mean, I put like these 4 figures here that shows it. It's so simple. It's extremely complicated, and it's in a very tiny part of your brain, which is the hippocampus. The whole thing happens in the hippocampus. So the boundaries the boundary cells define the dangerous regions. And in order to figure out how you move from one grid location to the other, the mammal provides a understanding of the heading and the direction, the heading direction, and how far it moved that integrates the path on this hexagonal grid. And then based on this, it generates a rasterized like map, which is a hexagonal rasterized map, based on where the mouse started the motion or where the human started the motion, right? So we can't do these experiments on humans, obviously, but with the mouse. So it's allocentric positioning observations. And then it extends this allocentric map by looking actually new directions that it hasn't explored before. So it's the curiosity of the mammal. It kind of goes to different directions to figure out. So we will be using a lot of these that you see here towards different phases of this presentation. And the curiosity part comes at the end of the presentation. So we'll introduce these concepts of how we can learn, how can we be curious and learn how to navigate on an unknown environment without knowing where we started, without knowing where we are going. Right, that's going to be the last portion. So, and a lot of the work that you will see coming up has been funded work by different, industry and then Department of Defense and NASA in general. So I like to build on that and then start getting into the details that my students have been working. I'll give the credit to my students. And they had done most of these. I was just guiding them. So in order to realize this information that the mammals do in the hippocampus, we like to build a mathematical model. So for this mathematical model, the environment modeling, we use a graph to model the environment modeling. For path integration, we use sensory data that's coming in. So this sensory data in this context is going to be camera and the inertial measurement units. Which both of them you have on your smartphone. So you have your accelerometers, you have your cameras. You can also put them on any platform. And then for figuring out where you have been moving into, we'll look at the landmarks. Like landmarks can be in the form of real objects, or landmarks can be in the form of important texture features in an image. So in using those, we fire our networks fire spatial locations through modeling of the neurons in an artificial manner. So we'll kind of talk about that also. All right, so the first part of the talk is architectures for self-localization on a map. And this was by a recently graduated student, Beng, who is now working on a startup company. He's published a number of work in this domain. So a lot of this is the contributions of Beng. So the network structure that we wanted to do for the mathematical modeling is a graph that you see here. This is the oval, right, on the left-hand side. And on the right-hand side, you see the mathematical representation of the oval. This is very similar to the GPS that you're using on a daily life, right? So you kind of have the GPS as a map, and the GPS breaks down the roads into piecewise linear segments, and these segments are connected using edges, which actually form something very similar to the thing that you see on the right-hand side. So now, then how are we going to use this model to figure out how we move? So we go back to the mammals again. So they do this using path integration. And the way they do this is by figuring out how much they moved and in which direction they moved. There are sensors for this on your brain, right? So the sensors, I mean, the neurons on your brain is going to be the direction cells and then the place cells, along with the grid cells. So they fire if you moved certain distances in certain directions. So we kind of use the same concept and use accelerometers and whenever available magnetometers or images to kind of provide this information for us, right? So the mathematical, I'm not going to get into too much of a detail, but I'd like to kind of keep this thing here. So which I'm going to jump back again, talk a little bit in more detail on this is a neural network. So we're replacing the neural network in your hippocampus with an artificial version of that neural network. There are two different ways we attack this problem. The first one is called a recurrent neural network. These are all artificial versions, and a graph neural network. So graph neural network in concept fits very well with the grid cell structure that we talked about. So you can generate a graph based on taking these locations that you see on the bottom side, these locations that you see, and provide nodes for these things. In our context, however, instead of doing this hexagonal structure, we are going to be doing this mathematical structure, the map structure that you had seen in the previous slide. So nonetheless, these neural networks, either one of these different cases of neural networks, is going to fire when it recognizes where it is. And then we'll use it as a positioning information. All right. So to represent the motion, in this particular work, we are going to be looking at several things. The first one is, as you start moving in one direction, the examples that you will see is a person walking on using a smartphone. It's not a robotic platform. In this case, we just wanted to kind of see if our method works. So this was a person walking using a smartphone in different directions. And then there's another example actually where the vehicle drives around the campus area. So, and then when you drive on in the campus, obviously the vehicle has to stay on the road. So that's why we are going to be looking at the road network, right? So the driving phenomena comes to a halt when you hit an intersection. And at that intersection, you have to make a decision to turn left, right, or go straight, right? So these are the actions that the platform will take. And then based on this, you start moving on the edge that connects these intersections. So you locate yourself on the edge. So there's a sequential set of nodes, a sequential set of turnings, a sequential set of edge locations that you traverse on. So think of this like your Google map. When you try to go from point A to point B, on Google map, you write, how can I go from point A to point B? And the Google map is going to tell you, you go on this road, come to an intersection, turn right, and then so on and so forth. So you kind of build up that kind of map. It's the same motion representation that we'll be using to figure out the location based on learning the map. So this concept becomes important. We are trying to, instead of generating a cognitive map, we are learning a given map using the potential motion pattern. So the first part of this is going to be long short-term memory networks for localization on the map. So the long short-term memory is not necessarily too important at this point for this talk, but just think of this as a sequence of information coming in, and that sequence of information generates a sequence of outputs. The inputs are the motion, the outputs are the positions, right? So then this input to output mapping is subjected to the cognitive map that we modeled, which is going to be this map that you see here. All right. So I didn't restart my presentation, so it shows like as if I had been on this for 43 minutes. I wish I restarted it so I know where, okay, I can actually look at that. There's 15 minutes, good. All right, so our input patterns for this particular case, we are looking at the heading direction and how much we move. So heading direction is represented by the angle you move, by the angle turn that you make, and the distance is by how many meters, how many inches, how many feet you walked or you traversed. So, and there's a sequence of these. So X becomes a sequence of these observations, angles and distances, angles and distance. At the output, I will provide a sequence of edges where the person is residing. So that's going to be between these intersections. Okay. So what you see here is on the left is my sequence of inputs. What you see on the right is the sequence of edges that I'm traversing as time progresses. All right. So this is just kind of tell you what happens in the background. So this is not too important, but just look at this thing. It's sequence of data coming in. These are the cues that are coming in. Passes through a network to generate the edge location. So it gives you a possibility of which edge you're on. So it's kind of a stochastic scheme in that sense. Right? Cues come in and then passes through a neural network, an artificial neural network in sequence to generate the edge location. The next edge location is going to be based on your previous location. So it's kind of like a one-time step. You look at one-time step before you to figure out where you're going to go next. So it's kind of a Markovian assumption. So these are these connections that you see here. All these arrows that goes from these circles in the right direction are these Markovian assumptions. So every time the neural networks makes an assumption, it uses the previous assumption, current input generates a new output. So, however, our problem is a little more complicated than a typical navigation problem that you know where you start and you know where your destination is. So here, I do not know where I start. So that's kind of the trick part here. So now, in order to figure out where you started, our conjecture is that if you are moving in certain directions, your motion pattern can only fit to the traversable paths on a single place on the map. So think of it this way. So if you look at the thing that's going on the left-hand side, there's like these blue dots moving, right? So you started at the beginning location that's given here, and you move a certain distance and turn right. Move certain distance and turn left again, turn right again, turn left again, so on and so forth, right? So the amount of turns you make and the amount of distances you traverse between these turns can only fit to a particular location on the map. So what you do is you start it everywhere. You don't know where you are. You start walking in all potential directions. And at the end, only one location is going to be left after you traverse a little bit of a distance. Typically, after you walk about in an open area, if it's a person, if it walks about 50 meters or so, we can figure out where the person is. If it's a vehicle, it typically is about depending on the extent of the motions, and after 1 mile we can figure out where the vehicle is in the city scale map. So just think of it from that perspective. You don't know where you are, you start moving around, and that your motion pattern at the end of the day can only fit one particular path that a person can take depending on the directions of motion allowed on the roads, right? So what you see on the right-hand side is the probabilities of all possible locations a person can be in, and then red is the highest, and it kind of goes lower all the way to blue. So that unfortunately, if you just use it like this is not enough. So you have to put that Markovian assumption into the picture. At any time instant, I can predict where I am, but it will give me multiple potential locations. Among them, only one of them is correct. So the question is, how are you going to figure out where is that correct location? So in order to figure out that correct location, you look at a sequence of the probabilities generated for each of these paths to compute a joint probability. So the joint probability is going to be getting higher for certain traverses versus other traverses. You can kind of immediately think about, oh my God, there's like hundreds of different places I can start with and potentially hundreds of different directions. So it becomes like a combinatorial explosion. There's so many places that I can be in at a certain time and I can move at a certain time. However, interestingly, in most of the experiments that we did, those incorrect locations and motion directions are pruned extremely fast after literally a few, minutes of motion. And then a lot of these things go away. You immediately figure out where you are and you stick with that solution. All right. So these kind of systems, as you can appreciate, as humans, when we are born, a lot of the activities that we learn over time is through experience. So, for instance, a baby trying to grab the Cheerios at first trial, 3 months old, 4 months, maybe 5 months old, tries to grab the Cheerios, and every single time tries to grab the Cheerios, they cannot grab it correctly until they find how to grab it. After that, when they put it in their mouth, it's not necessarily their mouth. They're going to put it in different locations on their face. And at the end, the reward is when they put it in their mouth, right? Then this process repeated again and again and again, we learn. So what we need to do for this particular set of problems like the humans do is we try to learn how humans or objects can traverse on the given map, on the traversable paths. So that's the learning phase. So like a human that learns over time, you like to train our network that we talked about so that it can learn how to move on the map. So for that, what we do is we generate, given the map, we generate many, by observing the direction, allowed direction of motion. For instance, in downtown, some roads are in one direction, right? So you cannot go both ways. So based on that information, we generated training corpus, and then this corpus or this data set of potential traverses that can happen on the map becomes our training set. So that means, unfortunately, in a way, that if I learn how to move in oval, I just know how to move in oval. I cannot get out of oval. I'm going to address that later on, but that means that you cannot use the brain or artificial neural network that is trained on the oval to the entire campus area with this method. Okay, so it's kind of the bottleneck with that. The way we do the testing is actually through other software that had been developed, in our group, that you kind of look at these images. So we look at here, sequence of images are coming in. From this sequence of images, you generate a traverse. So as the person turns, the image also turns, right? So, or the vehicle turns, the image turns. So you can use that information to generate these turns and to create this kind of traverse. This is called the raw trajectory that's generated purely off from these sensory measurements. But from this, and because our map is modeled as a mathematical model that looks at nodes and edges, the nodes are intersection, edges are the roads that connect them, we have to convert into that kind of setup. So we have a turn, introduce a node here, another turn, introduce another node, another node, another node. So that becomes now the map, the trajectory that fits on the map, right? So I'm going to use this trajectory to figure out where I am. I'm going to skip this. These are examples, right? So these are examples, and these examples actually initially is starting this traverse about 100 meters, and this is longer, a little bit longer. So in time, it gets longer and longer, and you can see that this particular trajectory maps onto this location on the map. So it can only map here on this particular map based on the distances and angles the person is making. Similarly, you kind of go over here and then over here. So I put one example here that if you do not use that Markovian assumption, it may tell you incorrectly that you were here in time t minus 1, like 10 seconds, and in 11th second, you jumped all the way to here. So those kind of inconsistencies can happen if you do not introduce those, Markovian assumption, which is the continuity of motion from your previous time instant. All right, so these are additional examples that we had showcased, that if you have your ground truth data that's generating this trajectory, this is the ground truth. This is your initial starting location. Look, there's so many starting locations that you see on these maps. Only one of them is correct. And if you do not use the temporal or Markovian assumption, temporal consistency, you end up in wrong places. It's kind of showing you that, which is different than the true location. So you see it's turning here, but it's actually going straight. So then you can use that consistency measurements to come up with the true result. These are two different versions that we proposed, so I'm not going to talk too much about that. So what I'd like to do is now kind of actually switch from this work to another artificial neural network representation of the potential hippocampus region to perform the localization on the map by mining. So you can consider this mining is not mining in literal terms. It's like you can consider like data mining. We are mining the map to figure out where we are, right? So it's like data mining problem. But in this case, the data mining becomes subgraph mining. Graph becomes the trajectory, right? So again, we have these set of mathematical model that we have. We talked about this. We have this information, which is the trajectory that we generate as the person moves or the vehicle moves. What we do now is a completely different representation of this. We like to create a hierarchical representation. So instead of using this as the representation like we did before, we like to convert this to another representation, which is more like the hierarchy that the hippocampus uses. So if you think about from a hippocampus perspective, there were like these grid cells that creates these hexagonal regions, right? So in a former slide, these hexagonal regions within the hippocampus actually is multi-scaled. So you have smaller and larger versions of this. So that means your brain, as you walk around, it has different levels of positioning. You know you are in Columbus. You know you're in Ohio State campus. You know I'm in Balsall. I know I'm in 214 city. These are different scales of position. So I'm kind of trying to create the different scales of positioning to create a modified version of this graph that you see at the bottom. So it's not that important now, but you can consider this thing is red and orange one distance or two distance. So if you consider this one distance, it is one distance to go from red to orange, but you can go back to this blue from orange and back to orange again, back to red. So you can, even though you think this is one distance away, you can consider 1, 2, 3, 4 distance away as well. So you create this hierarchical representation to modify the graph to this graph that you see at the bottom. And what do I do with it? I use that to create another space, an unknown space, a latent space that you see on the right. So this is an unknown space. I like to go from here to this unknown space, which actually is the thing that I will use to figure out where I am, right? So this is called a latent space embedding that actually encodes the geospatial locations for our problem in this case. We talked about this. So this thing works by creating that artificial networks. I have my input trajectory coming in. I generate this representation, and this is the neural networks that actually creates message passing from one node to the other. The message passing is my walking from one node to the other. And in the end, this is the locations on the map. So I can be anywhere on this grid location that you see here, right? So obviously the representation is not geospatial anymore. The representation is is a stochastic representation. And at the end, I will come up with probabilities for each of these potential locations and pick the best probability, which is called a posteriori estimate, and use it as my position. So don't need to worry about this message passing down here. So I think the examples make it a little bit more cleaner, but we looked at this in small scale, middle scale, and large scale. So small scale is our, the oval area. The middle scale is the campus area, and the large scale is even a larger area, which is composed of these grid-like structures, which is pretty complicated, as you can see here. So this is called a Hollywood scene kind of map, which is this grid-like structure, at least in our field. So if you look at this, these maps that you see here at the bottom, these are my mathematical models at the bottom. For the small scale set, I have 91 intersections. For middle, I have 115 intersections. And for large scale, I have 3,000 intersections. Connecting these intersections are the roads. If you look at this, on the small scale, I have 155 roads, and on the large scale, I have 8,000 roads. And this is, depending on the size, obviously, it's like a 10 by 10 kilometers square. This is 2.5 kilometers square. This is, I think it's like 1.6 kilometer by 0.5 kilometer. So then we will use this map information to generate all potential motion patterns on this map, which makes it really complicated task. If you look at here, I can generate 235,000 potential walkable paths on this map. Middle scale is, if you see, is smaller because of the traversable path information. Even though the size is larger, the number of roads are, the distance on the roads are smaller, so the traversable paths become 10,000. And the DC area, you can create like 644,000 potential trajectories to go from point A to point B. All right. So the rest is not that important. Now, there might be a question about this, that the whole problem, don't look at these numbers at the moment. I mean, just, I'll get to these numbers in a second. If you think about the whole process that we talked so far, looks at how much motion is needed to position yourself on the map. Because you start with unknown and you have to move around to figure out where you are. How much are you going to move? If you move a very short distance, you cannot figure out. If you just take one step, it's like you didn't take any step, right? So you have to move a little bit longer to figure out where you are. So this is kind of telling you how much you have to move, how many nodes you have to pass to figure out where you are. Just look at the large scale map. I think this result is more important. And it doesn't matter if it's filtered or augmented. Just let's look at the augmented case. If you just move 5 nodes, the probability of figuring out where you are correctly is 10%. It's very low. You have to walk a little bit longer. If you walk, instead of 5 nodes to 6 nodes, the probability increases to 24%. If you walk 10 nodes, it increases to 87% accuracy. So that means this method that we talked about is very much dependent on how much you move on the map to figure out where you are. Okay, and it increases all the way to 87% accuracy for large scale, 95% accuracy to middle scale, and 93% to small scale, depending on how far you walk. Right? And once you figure out where you are, you don't have to figure out again. You're done, right? So you can just go from there and find where your next step is going to be. these are the, setups that we had. That kind of Bing is walking with this phone around. This is the first frame. And we also put cameras on this vehicle, kind of collect the data for positioning the vehicle. Now, there are different, so far what we had seen is we were using heading and distance information. Heading and distance information can come from your magnetometer, your compass, and then compass, and then your inertial measurement. And so inertial measurement units, the accelerometers, you can integrate it over time to tell you how far you walked. So now we are going to augment this thing with one more information, which turned out to be very important for one of the projects. So we're going to introduce this visual data, the camera information on top of this. So that means now when you have the visual data, you will be doing the matching of the landmark as you traverse this map. Once you come to a landmark, you turn left or right, which is similar to the Google map, driving directions. But I'm going to use the landmarks now along with the distances that I traverse. So that means that turning and left and right actions that I make based on the distances that I traverse is now going to be augmented with the visual data that's coming in. My goal is to improve my results, right? I want to go from this 85% to even higher percentage with the introduction of these images. So instead of 2 sets of data, now I have 3 sets of data. But when you introduce image, when we talk about hippocampus, don't look at this slide again, details too much. When you look at hippocampus collects data from all parts of your brain. It considers the sounds you hear, it considers the thing you see on your visual cortex, it considers the information that was given to you in terms of how to walk around in that campus, for instance. So there's so much information that's collected on hippocampus. That means the hippocampus neural network actually is connected to a large, much bigger neural network that your brain connects. So that's why what we have to do here is to figure out a way to introduce this information that's processed on the visual cortex, right, to be a part of the network that we generated. So that is performed by a bigger neural network here that does not only look at the distance that you see here or the directions of headings that you see here, but it also looks at these images. So that makes it a larger network. So we're not going to get into these details here too much, but the attention-based neural networks becomes the model that can look at these images and associate these images with the potential images of the landmarks that were given to you. When you see this, turn left. When you see that, turn right, kind of information. And at the end, it comes up with the probabilities. So I'll skip these two. For this experiment, again, we did 2 different kinds of things. One of them was collection of the data for middle scale. We have these cameras on the vehicle collecting the data across the campus area. But for Washington, D.C., we couldn't go there and drive around to get the data. Instead, what we did was to use Google Street Side Images. So Google Street Side Images kind of provide you that information anyways, right? So we use that information as the visual information. We have the vehicle motion information from accelerometer and direction information from the magnetometer. So now all these come in, and then when we look at the statistics of these maps, it's not that important, but I like you kind of look at the potential lengths of the routes, and the number of routes you can go in is irrespective of the size of the map, follow a Gaussian distribution. So I like this to kind of be a model that I will be using at the end to come up with potential probabilities based on the distances that I traverse. So at the end, as we move from this concept to a completely different concept, I'd just like to show you these graphs here, and you don't need to worry about anything. Just look at this last part, the top right. This is telling you that if you use all sensory information, simultaneously, including distance, directions, velocities, and the images, everything simultaneously, then you hit the best performance. It's almost getting to 100% accuracy, right? So that's the message I'd like to give here. You need to use as much sensory information as possible. Right. So now I like to switch gears a little bit. We're almost getting close. Instead of trying to actually learn the map, I like to learn how to navigate irrespective of the map. Okay, so instead of giving the person fish, you teach fishing. Then look at it from that perspective. So UC has been working on this project, and it's still an ongoing work, but there has been quite a few developments that happened over the past 1 year. So look at this as a blind man concept, so analogy. A blind man is placed somewhere on the campus. He doesn't know where it is on the campus, and he is expected to reach a destination. Let's assume the destination has some kind of sound, so that you kind of walk around, and then if you walk in the wrong places, you potentially get a feedback you cannot walk there. So you actually start learning the map itself. So here we don't have the map. We're kind of learning the map, right? I'm gonna start at a position. I'm gonna go to a destination. I don't know how to go. I don't know where I started. I just have an idea of how destination looks like. Okay, so when I see it, I say, okay, I came. So this is maybe the last slide of the presentation. I have more slides coming, but think of it as it's like the last slide. It's not the last slide that shows the result. So you are kind of moving on using Google Street Side images on the Google Map. The Google Map, unfortunately, goes through the parking lot. They didn't align the roads well with the road itself. So it kind of traverses all these locations as it learns the map itself automatically. So everything here is completely automated, right? And then at the end, it finds the location. However, so the way this thing works is something called the reinforcement learning. So reinforcement learning, there's a artificial agent here, and artificial agents take actions. If it's traversing, it's taking walk this much in this direction kind of action. If it's playing a game like Pac-Man here, I loved playing it years ago. It's Pac-Man here, then it's going to tell you go in this direction, eat and get away from these ghosts, right? So that you don't get eaten. So, however, the environment is going to tell you you did it right or wrong. For instance, if they hit the ghost in this image, then you did something wrong. So that means you shouldn't hit. It learns not to hit, getting away from those ghosts. This has been widely applied for the gameplays. So there's a sequence of things happening. Action is taken, environment gives you a reward or a punishment and gives you the second observation. Then you take another action, and action has again a reward and maybe another kind of observation coming on next frame. So that's the kind of sequence of data that's given to you. You have the state, current state, you take an action, you get a reward and the next state. Take an action, reward, and the next state, and so on. So it's kind of rewarding or punishing the motions that is being made. In our case, the state is the image. So environment gives me an image through the camera, and I make an action. I'm going to either turn left, right, or go straight, right? And then if I hit something, I hope I don't. If I hit something, that's a negative feedback, right? So that means I shouldn't hit. If it, we are not putting this thing outside, hitting left and right to pedestrians. But if you get a pedestrian hit, then you need to learn, or you get close to pedestrian, say, okay, don't get close to pedestrian. The system learns not to get close to pedestrian. All right, so that's like the mathematical model. So what you see here is in the background, it doesn't know where it started. So it starts from everywhere and tries to go to a destination as it tries to learn the destination, because this is simultaneously happening. So in your brain, you can think of it as you make a motion, you make lots of other decisions with your motion. You don't realize it, but you make lots of decisions. Maybe there's a rock in front of you, you kind of go around it, right? So you take it for granted. But a lot of these probabilities are happening simultaneously, which we also do compute in this framework. And then close this second. And that way you find the destination. All right. Sometimes we might have multiple destinations. So learning that multiple destination framework becomes a harder problem. What you had seen is only just one target in the past. So we introduced multiple targets in the scene. Again, we don't know where they are, but once we learn by viewing them as a landmark, then we say, okay, this is our reward. We found them. So we're going to stop searching for the target again. So that's how you learn the map, learning, finding the targets. This is, one of those. So as it moves around, it's multi-target, the target changes, and then it learns how to move to the C target. It starts with A, the target was B. Again, there's a lot of process in the background happens to learn this motion. You're just seeing the last phase of the learning process that shows you the result. So another example, medical center. All right, so it may happen that as you start learning something, whatever you learned might become useless because there is actually dynamic changes in the scene. For instance, in this example, we learn, but then all of a sudden the road closes, right? So you need to relearn again, multiple times. So this relearning process in our framework becomes a pretty straightforward framework because we already learned part of the map as we traversed. So you're just extending that information. This is kind of showing that we are able to readjust our learned model, these networks, to ensure that we can come up with to the destination, even if there's dynamic changes in the scene. I will come, maybe I'll just quickly finish this up in the maybe next 3 minutes. So road is great, but what if you apply it to UAVs? These drones. So a drone can fly freely in the air, so it doesn't have a road structure, right? So the concept is similar here. You can move freely anywhere on the map, but where the motion becomes continuous motion, you can just go at a certain angle. Observations are images, and then the action that's made by the agent is, again, move this much in a direction that's similar to the vehicle motion, right? So just skip to this. Why don't I skip to something that's more important that I wanted to talk about? This is very similar to the road example. I mean, it's a repeat for the drone. So you can ask me questions on this if you like. But what I like to do is I like to actually talk about, maybe I'll just show you this. This is the final result that we generated. The destination is this landmark here, this set of buildings. So drone starts with an unknown location and then finds the best route to go to this destination after a number of learning iterations. And then you will see that actually, it finds that destination and then it stops flying. All right. I wanted to talk about the learning to navigate part. So this is that last part. My goal in this entire set of years was to actually come up with an agent that doesn't really learn just to navigate in one environment, just to come up with an agent or a platform that can navigate in unknown environments. That was the previous goal, which, it took maybe years to figure out, but finally we are there. that we learn to navigate in one environment, we can transfer that knowledge to navigate in a completely different environment. So the way we do this thing is to teach how to navigate. So for this, we define again like a map, as you see here, this is called scene A. And in scene A, I'm not interested in this map. I'm just looking at potential small set of regions here. Okay, these red regions, to learn to navigate in these random regions to random targets from random starting positions. So I start with this, in this case, I have like 7, 8 of them. I start with this 8. If I learn on this 8, the question is, can I navigate in this scene A, which is where they came from, or in scene B, which is the completely different place? So that was the goal. And then we were actually able to perform this thing that, we came up with a learning scheme called meta reinforcement learning, which learns how to navigate in these small places, which is extended to learn how to navigate in these larger places. And then we can shorten the learning time significantly. This is the iteration number from 70K iterations all the way to 4,000 iterations. This run pretty fast, by the way. I mean, when you see 70,000, it's not really too high in the environments that we run these things on. Then we extended this scheme to actually improve even further. And then UC came up with this incremental self-adaptive reinforcement learning scheme, which can improve the previously defined algorithm significantly. So the way it works is it combines the meta learning cycles. So don't worry about this. These greens are meta learning cycles, learning to navigate, with navigation learning cycles. So this is learning on the map. This is learning on the learning to navigate. So it kind of does this thing in a sequential order to really significantly improve the time to learn. I'm going to leave this last slide here. I am in this thought of view. So there are two thoughts of, ideas on machine learning. I'm just going to leave you guys read this thing. So it's really dangerous. It's really useful. So we have to do the right things to make it, make the best out of it. Think about these platforms that I'm talking about. Learns to navigate anywhere on the earth, underground, underwater, and then thinks these are weaponized. It becomes extremely dangerous at that point. So, and then there's so much, information that's not correct going on the web that affects. Those are generated by bots. These are automatically generated. Right. So I think there's so much good things about this, but there's so many bad things about it also. We just need to be careful. Thank you.
Well, thank you, Alper. I really invite folks on the call. I think given the size of our group today, I invite you either to raise a hand or to drop any questions that you have in the chat box. Well, maybe I could start with a question. So really fascinating demonstrations. And I love that you've added the visualization into to be able to see what the end product is from the complexity of the software programs that you have that are following these navigation strategies. And I'm wondering, what are the next steps? And maybe there's some plans that you might have as far as helping to integrate this into real solutions. So one could imagine a robot that's crawling on the road, and I may have misunderstood for your unmanned autonomous vehicles, whether you actually have these platforms flying on drones, but maybe you could sort of speak to, how the ability to do this navigation might then translate into applications that we would have in a real world setting.
Yeah, so the next step is the Skynet. we are trying to, I mean, you can look at this thing like this. So right now, UC is working on putting these things on a robot to kind of do the learning and learning to navigate on in unknown environments. And this can be indoors, which is what she's doing right now to actually learn to navigate indoors first, and then going into outdoors using the approaches that you had seen here. So the idea is to have self-navigating platforms without the necessity of using the necessity of the map information that you had seen in the previous slides. So we kind of generate maps as we move, and then we learn how to navigate on those maps as we move. So that's the goal. And then we are now working on a very simple platform, a robotic platform that's hopefully going to realize this thing soon. All this information that you had seen here, they run on the computer without the platform moving. So that means I pre-collect the data for all these possible routes, and I use them to do the tests and the trainings. So that's going to be the next thing. But again, I mean, if these things really learn self mapping the environment and moving around, so I don't know what's next. We'll see. I think I think I'll retire at that point. And you guys can throw me questions about, uh, how come I started thinking in this particular direction. I think AI is extremely dangerous. I work in AI. It's been like almost getting close to three decades now. My research has been on machine learning for the last 30 years or so in different aspects. But with the latest developments in the field, you might have heard Facebook has closed a section in their AI group that generated two separate machines that were communicating with each other. They couldn't understand what the communication was. So they stopped, they pulled the plug on both of these machines, and they dismantled the program. So, with this chat GPT becoming a daily part of students' life, 100%, in our lives, so it might be used with rogue agents to actually confuse them, to generate false data. So they learn over time. So you can confuse them. It's not too hard. So that becomes a really dangerous game to have an impact on human health, environmental issues, on anything you can think of, I think. So I'm kind of a little bit skeptical with the, even though I work in it, I'm being hypocritical here, but I'm kind of skeptical about what is next. And it might be really bad. It might be really good. As long as we use it right, it would be good, I think.